Hi, my name is Jose Villazon, and this is my Physics 1 lab report. A little bit of introduction to this lab. So the purpose of this lab is to observe the motion of an actual physical object moving at a constant velocity, and we're also looking to compare our scenarios' real-world data to the predicted data by our computational model. Some principles we'll be using in this lab are Newton's first law of motion and Newton's second law of motion. A preview into some of our observations and results. Assuming no external forces like friction, our object will maintain a constant velocity through the entire video clip. Comparing our data, in the end, we see that the computational model lines up pretty well with our real-world data. So some main principles and ideas we'll be using in this lab. Newton's first law of motion states that an object of motion stays in motion unless acted upon by an external force, and an object at rest remains at rest unless acted upon by external force. We see this every day in our interactions with objects in the world. And this is especially important because when there's a net force of 0, we will have a constant velocity, so therefore the object will neither speed up nor slow down. And then Newton's second law of motion further proves this, as it states that the net force acting on an object is equal to the change in momentum of the change in time, which gives you F net equals dp dt, and is more commonly known as force equals mass times acceleration. And since F net equals 0, we know that acceleration equals 0, and therefore constant velocity. And then we will also be using the position update formula for our code, and we'll also be using the velocity update formula for our code as well. So for the experiment, we used an expo marker as our system, and the surroundings were just the floor. Our initial position was at negative 0.431 meters, and it was negative because the origin wasn't moved in tracker. And our initial velocity was found by finding the line of best fit between the points on this graph, and since velocity is the rate of change of position, all we had to do is find the slope of the best fit line, which was this value here. So now moving into the code, to make an accurate model of our real world data, we have to input some initial conditions into our code, as seen in the top picture. So we just input the values that we found in the previous slide and input them into our code. And then once the object was in motion, we use the code in the bottom picture to update both our velocity and also update our position. But since F net equals 0, the velocity will stay constant, and that's why we're adding the 0 vector here. But then the position will update since it is moving with a constant velocity. So data versus model, this was the graph outputted by our computational model, and then this is the output of our real data. And we can see over here, this is an overlay of both, and the data in purple is the computational data, and the data in pink is the real data. And as you can see, it's mostly linear, which shows that our computational model was a pretty accurate representation of our real world data. So some possible sources of error in our lab could have been inputs into the tracer software. Our tracking points might have not been exactly right, or we could have maybe put it on a spot where the velocity slightly changed a little bit with our marker. Other possible sources of error could have been friction of the ground and interacting with the marker, and also possible air resistance that the marker could experience, which would have resulted in a non-zero net force. So with our what if and what does this mean questions, so the what if question, what if we change the axes or the origin in tracker, and would anything change? No, the results would stay the same. You still get the same graph that we had in the slides that I showed you previously. The only thing that would change is the numbers that make up that graph. And for the what does this mean question, it asks if we could find the forces that make up F net equals 0, and in the y direction, yes, you can, because you have force of gravity and normal force, which gives you a net force equal to 0. However, in the x direction, it's slightly trickery because you have to consider force of friction and possible air resistance, which would lead to a non-zero net force.